Okay, so this is a digital system question that I did. So for this question, it gives a very long chunk of explanation about integer division and remainder. So essentially what I can boil this down to is that basically usually the hardware we usually deal with, it just takes the quotient and then the remainder. The quotient is when it usually rounds down, and then the remainder is always a number between 0 and whatever the quotient is between that range, right? But however, here we're more interested in the C language. We want it to kind of um, the answer to go towards 0 when it's signed. So for the positive numbers, we don't have any disagreements, but for negative numbers, there are some disagreement. What I mean by here is, let's just do an example. If we were to divide -1 by 104, 1024, then the hardware usually would give something like this because it sees, okay, it's negative, so it's going to give -1 as the quotient. The remainder would be something positive over here. But in this sense, we want to round it to 0, the answer quotient to 0. So instead, we would round Q to be 0, and then the remainder would be something negative. That's the version we want to implement. So yeah, so we're trying to implement the C version using assembly. And then obviously the positive side have to hold, of course. And then the negative side, the remainder should be also negative. So that's the idea. That's the version basically that we want to show over here. So in part A, we have defined mathematically the functions binary A and two's complement that map a string bit string A to the integer it represents according to the unsigned and signed representation, respectively. We haven't even gotten into the part of implementing that. It's basically just going through definitions of what we need, right? So let's just assume that we have a 32-bit number that looks something like this, where AI is a 0 or 1. For the unsigned bit, we're going to use all 32 parts, right? So then it just be the first digit over here, A0, is 2 to the 0. The next one is 2 to the 1. The next one is 2 to the 2, so on and so forth. And the last one is 2 to the 31. So I'm just going to times whatever 2 to the whatever power to A and just sum everything together. And this would be my binary representation. For the signed in, taking the approach of the two's complement, I just take whatever is in the front, the first bit. The first bit just represents the signed number that was negative. So then it just be negative of the first signed number times 2 to the 31, and the plus whatever parts that remain that are basically unsigned. So yeah, that's A. Part B, we're asked, in terms of your answer to your previous part, show that the logical right shift instruction thus computes in register 1 the correct quotient A divided by 2K, where A is the unsigned number initially in R0. So basically, how you kind of think of it is, okay, if we had let something to be an unsigned number, right, it looks something like this. If we were to divide it by 2 to the k for each one, then what we essentially do is we just take each one into that and then just subtract it by k because we're representing each one as binary, right? So it's 2 to the something power. So we just subtract that part. And then we just have, we can just split up the sum to be differently, right? The first part is our quotient, and then the remainder of the part, because for the part that I is smaller than k, then this part basically goes to 0 because there's nothing left, right, of integer division. So this part is 0, and this would just be the quotient. So yeah, so that's how it works. Um, LSR just stands for logical shift right. And then part C, we're asked to show how the remainder R from the division of A divided by 2K for unsigned A can be computed using a pair of shift instructions. On a RISC architecture, what might be the advantage of such a pair of instructions over simply masking with a value 2 to the K minus 1? Okay, so this is broken down into two parts, right? How to implement this and what the masking versus this does, right? So the first thing is, okay, if we're thinking about this as a number, right, that is 2 to the 0 all the way to 2 to the something over here, right? Each one is increasing. So the parts that we want to keep is just, we just want to have something over here, right? We're just going to shift it all the way to the left. And we just preserve it and shift it up to this point. So everything over here would just be essentially canceled out with the zeros. And then hence afterwards, we would just shift it right back again to the spot. And then we would get the remainder of what we need, right? This is pretty straightforward. So this is exactly what we're doing. We're just logical shift left from R, we're going to store it in R1, R0, and then this is the number we shift by because we want to keep 32. We move 32 minus K, so we keep that K part. And then we shift it back by the same amount, right, to the right. So hence we just basically, in other words, we just erase this chunk over here to be all zeros and get it back to that spot. And why is this method better than, let's say, masking by 2 to the K minus 1? It's because in 2 to the K minus 1, if our K was relatively large, then 2 to the K minus 1 would be a pretty big number to store, right? So we need to actually store this number, load this number, and then do the end. So that means that we're going to literally take more steps than what we currently do with just shifting. Because shifting, we just need two registers. We just do one step of shifting to the left and then one step shifting to the right, which is very easy. Whereas the loading, then the storing, then the end would take more steps, especially if K was large. So that's kind of the advantage of shift over masking. Moving on to part D, copy the code from figure 1, adding comments to indicate what values as a function of A is computed by each instruction. Show that the value returned by the function agrees with the specification in all cases. So this is what we have, the code over here. Basically, the function we're trying to implement is remainder of 1024. Take A, and then we return the modulo of that. And we have these functions. So I'll kind of walk through it. So the first instruction is ASRS, R3, R0, number 31. So basically what this does, essentially, is it copies the most significant bit to fill up the empty space. So what this does is, suppose we have a number over here, right? This is the most significant bit over here. It could either be 0 or 1. If it was 0, then we shift it 31 spots over. Then it would just be a whole chunk of 0. So everything would be 0. So if everything was 0, then we just have 0. And if it wasn't, if it was 1, then ASRS basically shifts the most significant bits over. So then it would just look something like this, where I have a whole chain of everything is 1. So by 2's complement, this would just mean, okay, I have something of this plus everything over here. So then my number would just evaluate to -1. So yeah, my result would either be 0 if it's positive, or -1 if it was negative. So yeah, that's what I have. And then basically I just store this kind of flag that I created inside the register R3. That's the idea. And in part 2, what I do is LSRS, R3, R3, number 22. So I'm just going to check, right? In the case that it was positive, so R3 is equal to 0, then doing this shift would do nothing, right? I'm just shifting a bunch of zeros, nothing happens, so it's still 0. If R3 was equal to -1, then what this does is shifting it by 22 would get me to the sequence of 0, a bunch of zeros, and then resulting in a bunch of 1s in the end. The 10 ones would essentially create the number 1023, which in binary is just basically the number 1023 in my case. This is my bias, which is 2 to the K minus 1. My thing was 1024. 1024 minus 1 is 1023. So then the third case, what I do is, okay, 1 and 2 just basically creates my 1023 bias. This just creates my bias, these two steps. And then what I do is, okay, I have my number 3 step. So I'm going to add R0, R0, R3. So I'm going to, again, break it down into two cases. If it was positive or 0, then my thing would have been 0, R3 would have been 0, right? So I have no bias, so I'm still kept at A. Otherwise, if it was less than 0, then my thing would just be a plus 1023 from before, right? So I'm just plussing the bias to my th initial thing. Then what I do for part 4 and part 5 with these shifting instruction is just the part from earlier, right? I'm just taking the modulo operation by 1024. So I'm just taking the shift left by 22, then shift by 22 again. So what I'm doing is if A is greater than or equal to 0, I'm just taking the modulo of 1024. If A is less than 0, then I'm just taking A plus 1023 modulo 1024. That's what I'm doing. In part 6, what I do is I want to remove the bias from my number. So I'm just going to subtract it from the number. So if A was greater than or equal to 0, my bias was 0. So if I subtract by 0, nothing happens. So I still keep my remainder. If A was smaller than 0, then I would just have this expression, right? Whatever remainder I just found from before, I subtract it by 1023. And then in the end, I return whatever I got with that remainder. So why does this kind of method check out, right? Why is it true? So I kind of wrote down a proof of why it works. So in the positive scenario, we have A greater than or equal to 0, so the sign bit is equal to 0, so R3, our bias, is equal to 0. The shift basically isolates the bottom 10 digits, so it computes modulo 1024. Subtraction by 0 does not impact the final answer, so everything checks out, right? As a negative case, that is kind of a bit more complicated and why we had to go through so many more steps. For A is smaller than 0, R3 is all ones, which would have the value R3 is equal to -1 from our first step, right? And then we left shift, right shift, logical shift, right, but right, I can't even say it. But basically, we're just shifting it right by 22, which makes it 2 to the k minus 1, which would create our 1023 bias. Then what we do is we can essentially think of A as the quotient times 1024 plus the remainder, right? Which in math would have been something from 0 to 1023. But in our C specification, R is negative, so we would want something of the form R minus 1024, unless the case that R is equal to 0. Um, so what we do here is we want to add the bias to the thing. So then we just do A plus 1023, which essentially in our original form would have been Q times 1024, the same, plus R plus 1023. So then we would take the modulo, which means this number is modulo 1024. So then we would have this expression mod 1024. So if R was equal to 0, then we know that the answer must have been 1023. And if R is greater than 1, we would have gotten this, which would be R plus 1023 modulo 1024. Because R is greater than 1, we know that if we mod this, it's going to be negative. So hence we know that the remainder is just R minus 1. So yeah, it would just either be this case. So when we remove the bias, which is 1023, if R was equal to 0, then 1023 minus 1023 would be 0. And if R is greater than 1 or equal to 1, then we have R minus 1 minus 1023, which would have been R minus 1024. And it checks out because before in our remainder, it would have been positive, right? Our R from before was from 0 to 1023. And in the case that it's not equal, it's greater than or equal to 1, so it's from 1 to 1023. So that if we subtract that, it would have been the negative remainder that checks out. So that's why it works. I think it's pretty clever in the sense that we have this code, and basically we're just taking advantage of, okay, we first have this, which is like the core base of the modulo, right? And then we have the first part of this, which is creating the bias, and then adding on that bias, and then making sure that we remove it at the end. So that's what the code does essentially. And then in part E, we have give similar branch-free code for a function that returns the quotient on dividing its signed integer argument by 1024 and justify your answer. Okay, so we're finding the quotient, right? So our approach would be somewhat similar, except with a bit of modification to it. So let's just call our function. We're going to call it div 1024. What we do in the front is the same, right? We want to keep the flag, basically ASRS, that would give us either 0 or -1 as before, the same idea, right? And we're going to create our bias, which would be the same step as before. And then we're going to add it on to our number, which would be the same step as before. And then the thing that changes is that over here, we're going to do a arithmetic right shift. So what essentially happens is that we're just taking the A plus bias, dividing it by 1024. And then we just directly return it. The change from here is that, okay, this is the major change, right? ASRS, and then we see one more change is that there's no subtraction function. It doesn't exist here. Why is this the case? Because essentially, we don't need to subtract because the 10 bits are already destroyed from before. Because in the earlier case, when we were looking at the remainder, we still kept the bias, right? Inside here, because we're doing the arithmetic shift right, then that means that everything that was before, let's say the 10 bits that we kind of divided by 1024. Let's say our thing looks something like this, right? This was our quotient, and this was our remainder, right? We can think of it as that. So what we essentially did, if we're shifting it right, is that we have just moved this chunk over to this spot. So this would be the end of the thing, and everything here would be gone. So if it's gone, then we don't need to subtract it anymore, right? So that kind of makes sense. So yeah, a more formal proof of that is that if it's positive, then we don't have to kind of deal with it. If it was negative, then we kind of have the case that A is equal to Q times 2 to the K plus R. So then what we can do is something like this, right? We can do um, inside our bracket, we have the bias. So we're going to do A plus the bias divided by 2 to the K. And then we're going to take the floor of that. And then what we're going to do is we have a bracket, then we just expand out what A is, right? A is this thing over here, Q times 2 to the K plus R, and then we have this remainder part of the bias divided by 2 to the K. So then that leaves us with basically we can extract out. We see that there's 2 to the K here, 2 to the K here, so we can extract that out. So we get Q, and then we get this chunk over here. So for the case that R is equal to 0, then if we have no remainder, then this part just evaluates to this. And we see that 2 to the K minus 1 divided by 2 to the K, and the floor of that is equal to 0, so we get the quotient we need. In the case that R is greater than or equal to 1, then we get this, right? So then this would have made it such that R minus 1 would have been greater than or equal to 0. So then this thing would have evaluated to 1. So we would get Q plus 1, which would be what we need. So yeah, basically, in other words, our quotient checks out, and we don't need to subtract it because of this argument that it's already destroyed. So ASRS is really a really nice way of kind of doing the shift as well as just making sure that nothing gets destroyed. As well, we do ASRS because the sign bits is preserved. Because if it was just a logical shift, and let's say that it was negative, then or positive, it wouldn't have mattered. But if it was the case that it was negative, then we definitely want to preserve that part. So the arithmetic shift would have been a much better choice. Cool, let's end off here. I think the major thing to take away from this question was just kind of the nice use of ASRS to kind of keep track of the flag of the sign number, and then using the property of having a bias, adding that bias, and then removing that bias if needed. Let's end it off here.